We want to look at differentiation under calculus, and we are going to consider power function rule to start with. My name is Bosun, and you can always call me should you have any inquiry on this particular topic. Now, by power function, we have problem like y equals to a x is power n. X is the principal variable here, n is the power of x, and a is the coefficient of x. Now, to differentiate this, the y dx is derivative of function of y. Now, to do that, we have to bring the power, which is n here, to multiply the coefficient of x. That gives us na, and now we raise x now to a new power, which is 1 deducted from the old power. So at any point in time when we are differentiating a power function like this, we simply multiply the coefficient by the power to have na. That gives us a new coefficient, and at the same time we deduct 1 from the old power to have a new power. That is the simple rule of power function in differentiation. For example, let's take example 1. Example 1, assuming we have y equals to x. Now, it is obvious that the power of x here is 1 and the coefficient of x is 1. So dy dx automatically will be the power, which is 1, times the coefficient, then times x raised to power 1 minus 1. And that gives us x raised to power 0. And from indices, anything raised to power 0 is equal to 1. Therefore, the derivative of y equals to x is 1. That is the simplest example that we can have on power function. Now, we can consider another example where x is now raised to power of 2. That is, we have y equals to x squared. If y equals, that's example 2, y is equal to x squared. Now, dy dx will be equal to 2 times 1 x is power 2 minus 1. Remember, the power will come down to multiply the coefficient, and at the same time the power will reduce by 1. So we have 2x is power 1, which is what? 2x. So the dy dx of y equals to x squared is definitely equal to 2x. We try as much as possible to consider as many examples as we can within the context, the space of limited time. Let's say we have another situation where y is going to root x. It becomes very easy for us when we rewrite the function as y equals to x raised to power half. That's from indices. Anything, when you are finding square root of any variable, you can raise the same variable to 1 over 2. So we can now get the derivative of the function as 1 over 2 x raised to power 1 over 2 minus 1. And that gives us half of x raised to power minus half. And then that becomes 1 over 2 times 1 over x raised to power half. Then finally we have 1 over 2 root x. So when we differentiate y equals to root x, we first rewrote it as x raised to power half. Then we differentiate using normal power function rule, and we arrive at 1 over 2 root x. We have been applying the basic knowledge of indices all through the questions that I've been solving up to now. Now we'll take the last example. Example 4, we have y equals to 3 into cube roots of x. Now, with the head of indices, we can rewrite it as 3x to the power 1 over 3. Cube root of x means x to the power 1 over 3 from indices. Now, we can now differentiate easily using power function rule. That is, the power, which is 1 over 3, will come down to multiply the coefficient, and at the same time the power will reduce by 1, that is minus 1. So we now have 3 cancel 3, so we have x to the power 1 over 3 minus 1 is minus 2 over 3. So we have 1 over x raised to the power 2 over 3, giving us 1 over cube root of x squared. So when we differentiate y equals to this function, and we wrote it as it in indices, this is what we are going to arrive at. Now, the final note that we need to take here is that whenever we are differentiating a constant function, for instance, if y equals to 2, the y dx will definitely be equal to 0. Whenever a function is being differentiated, the derivative will be 0. Even if it is 20, if it is 50, if it is 100, the y dx will always be 0. That is the basic rule about power function. Thank you very much. I wish you all the best.